Hey guys, here's the spiral review for Spiral 3. First thing says no calculator is needed, allowed, or even available in the spiral. That is not an accurate statement. That's a holdover from the document that I originally used a couple years ago to make this. Calculator is totally fine here. Just be sure if you need to show me work that you show me work. Okay, first up, let's talk about functions. We're looking at function f, consisting of 4 segments listed below. The first thing we want to talk about is what do the open circles at some of the endpoints mean on this graph. It means that those endpoints don't exist. The graph goes all the way up until we reach each of those places and just stops there. The reason that this happens is actually just to keep this a function. Because if I were to do a vertical line test here, it would go through the point, then go through the hole, and because it's a point and a hole instead of 2 points, that's okay. So this still passes the vertical line test, even though it looks like it might. The domain of this function, we want to think about all possible x values. Well, the lowest x value on here is going to be -2. And then I'm going to continue. It looks like I have a gap in the domain, but really, I'm going to zoom in here so I can see this a little better. Really, that's not a gap. What's happening is we're jumping up, but we're not losing a value here. So as far as domain goes, this function is just kind of continuing onwards, and my function exists all the way from -2 up to +2. In terms of indicating this at an interval, I might do this with 2 closed endpoints because my both endpoints exist. The range here, I say it's less tricky, but it's also a little bit more tricky because the range only exists at very specific values. So the range exists here, and then again here, and then again here, and then again here. And what we need to be aware of is that in terms of the range, because it's 4 specific values and nothing else, we have to list those values separately. So -2, that's my lowest one, then -1, and then 0, and then 1. I could correctly use squiggly brackets here, but I don't need to. Again, let me just talk about the difference between these two. The first, we talked about some kind of an interval. Apologies for the barking. So the first part, this is some kind of an interval because even though these are separate pieces, they form something that keeps going and doesn't have any breaks in it. The second one, we're going to use individual places because we have gaps in the y values. We have -2, we have -1, but we don't have anything in between. So it is not correct to use an interval to describe this. These are 4 separate points. This is a range of points. How could we modify our function so it's no longer a function in 2 specific places? I think the easiest thing is I might plug those holes. And for that, I'd be adding a point at 1, 0, and maybe at 0, -1. There are tons of other ways that I could do this. Most of them involve something like adding a couple points somewhere on these things. For the next one, we've got relation n. I've got to approximate the domain and range. I went for a pretty picture instead of one that makes sense as far as finding domain and range. And it doesn't quite end up at 3 or at -3. It's a little past that because that's where that seems to have endpoints. But that's pretty close. So my domain for this might be something like -3 to +3. And it looks like that hits those points, so let's call it that. And I'm going to approximate the range. Well, there's -1. Maybe -0.5 is the lowest. And up top, well, we've got somewhere between 4 and 6. In fact, that looks like exactly 5 on the dot. So we need -0.5 to +5. And that looks like a pretty good domain and range for this graph. Is this a function? based on what we know about functions, this is definitely not a function. It does not pass the vertical line test. And that would be enough to say something like no, and that it fails the vertical line test. Another argument for this could be made if we were studying a different type of math than we are. We're talking about things on a rectangular coordinate grid. Excuse me. If we have a chance later this year to look at something called polar coordinates, we're going to have to reassess our understanding of functions, and this may fall into that category. But based on what we know so far, this is not a function because it fails the vertical line test. For the function section, here we're looking at some problems that are combining functions on tables and functions from points. So for f of g of 3, first thing I've got to do is find g of 3. G of 3, g is the lower graph, okay, so g of 3, 1, 2, 3, equals negative 1. Since I'm finding f of g of 3, I'm really finding f of negative 1. Okay, f of negative 1 is equal to, so I'm going to use the top graph, and negative 1 has a value of 0. G of f of 3. Now I'm going to start from the inside. F of 3 has a height of 2. I'm going to plug that in, g of 2. And there's 2, has a height of negative 3. F minus g of 2. In other words, f of 2 minus g of 2. Well, f of 2 is 2. G of 2, so I'm finding g of 2 is negative 3. 2 minus negative 3 is 5. G of f of 0, work from the inside out. F of 0 is 2. Now I'm going to look at my next layer. So that's the g of f of, and f of 0 was 2. So f of 2, we already found out was 2. Nice. And now I need g of f of 2 is the same as g of 2. So g of 2, and that's equal to negative 3. Looking at our next one, we've got 2 times f over g of 1 plus 3. So let's find f of 1 over g of 1 first. F of 1 is going to be 2. That keeps coming up, huh? G of 1 is 3. And we're going to multiply that times 2. So 2 times 1/3, and then we're going to add 3 to that. So that'd be 3 2/3. If you wanted to leave that as a improper fraction, that'd be 11/3. 2f of 3 minus 3g of 2. Okay, 2f of 3 is going to be 2 minus 3, and g of 2 is going to be negative 3. 4 plus 9 is 13. Now we're into transformations. I'm going to do the x stuff first. So I'm going to go negative 9 is equal to the inside. That's x plus 1. That new point is going to be 10, or negative 10 rather. My other point, 5 is equal to x plus 1. That means my new x value is going to be 4. Let's look at my y values. I'm going to multiply the y times negative 2 and then subtract 3. My first one would be 3 times negative 2, negative 6, minus 3 is negative 9. And my second one would be 5 times negative 2, minus 3, which would be negative 13. So you might say these are being moved left 1, the y's are multiplied by negative 2 and then being moved down 3. Unfortunately, neither of these will show up so well on our graph. One of these days I might give you something that actually graphs on there easily. For our next one, we do the same thing. I might add a third point here of negative 2 comma negative 3, just because it's nice to have the vertex, and go piece by piece. So first point, negative 3, negative 2. I'm going to do the x first. Negative 3 is equal to negative 2x. X is equal to 3 over 2. Now the y, I've got negative 2, nothing being multiplied, plus 2 for the end of this is equal to 0. My new point would be 3 over 2, comma 0. So that would be here. Second point, let's take a look at that vertex. So we're looking at negative 2, negative 3. I'll do the x first. Negative 2 is equal to negative 2x. That means that x equals 1. Now I'll do the y. Negative 3, there's no multiple, so just plus 2 equals negative 1. My point is positive 1, comma, negative 1. And finally, we've got a third point, 0, comma 1. I'll do the x first. 0 is equal to negative 2x. That means that x equals 0. And we'll look at the y. The y is going to be 1 plus 2, which is 3. So 0, 3 would be that point. Let's plot those points. So 0, 3. My vertex is at 1, negative 1. And I've got a third point at 3 over 2, comma 0, which is there. So if I connect those, it's going to look something like this. A skinnier parabola that has shifted and looks like it's flipped around some. And finally, we end up with polynomials and their graphs. We've got a sketch, a graph. The two skills that you need here are sketching a graph and writing an equation for a graph. And both of them kind of use the same type of understanding. As a hint, you might have to go backwards on your spiral. Based on some points, you might have to make an equation that looks something like this. Okay, so sketch a graph of the following polynomial. I've got to identify any intercepts and describe the end behavior. I like doing the end behavior first. You've got a positive number out front in terms of x's. I've got 2 for my degree here because of that exponent. I've got 2 for my degree here because of that exponent. We've got 1 because there's no exponent there. We're talking about a degree 5 polynomial. Okay, that means that we're odd. That's going to either look like from bottom left to top right, or from top left and go down to the bottom right. Because it's odd, we know that its ends have to go in opposite directions. Because this is positive, it's going to go up and to the right, which means I'm going to go down and to the left. Let's see what else we can get from this. I'm going to look at intercepts next. First, we're going to have positive 2. And because we've got a second power there, I'm going to put a point and I'm going to write bounce. Wherever we're coming from, we're going to bounce off the graph there. My next one, we're going to have it x at negative 1. And I've got another double exponent there, so we're going to bounce here too. And finally, we're going to have x at positive 5. So 1, 2, 3, 4, 5. This does not have an exponent, so it's just going to be a pass-through. In fact, my graph might end up going up and to the right like that. And when I draw it that way, I certainly do not need this extra arrow going nowhere. I might continue this, and my goal is to draw a nice smooth curve through here, so we're going to go down, up. I'm going to bounce off the axis. I'm going to go up to the next one, bounce, and you notice I end up heading back down. This is a pretty good graph for what we're trying to do. The other pieces that I might need from this, because I know I need to identify the x-intercepts, which are at 2, -1, and 5. We talked about the end behavior. This one is going to rise to the right, and it's going to fall to the left. That would be totally fine. If you'd like to do the approaching notation, this would be x approaches infinity, y approaches infinity. I can't write today. And this would be as x approaches negative infinity, in other words, goes to the left, y approaches negative infinity. That does leave the y-intercept, and to do that, we've got to look at our equation and try plugging in 0 for x. So for the y-intercept, we got y is equal to 3, 0 minus 2 squared, 0 plus 1 squared, and 0 minus 5. Okay? And once I do this out, we get 3 times negative 2 squared is positive 4. 1 squared is 1. And we get 0 minus 5 is negative 5. 3 times 4 is 12, times 1 is 12, times negative 5 is going to be negative 60. So y-intercept is negative 60. Might be nice to fill that in my graph as well. So negative 60. And just to make myself honest, I'm going to use 1, 2, and 5, just so we can see where those points are. Okay, number 7, we're onto the quadratic part. You're going to have some kind of a word problem. I would not be at all surprised if it had to do with some kind of defense, because that seems to be a pretty good way for us to get a visual of this. So you've got a 1,200-yard roll of fencing. In a field along a river, you want to make 3 pastures where zebras can roam peacefully, divided by dividing a rectangle vertically into 3 equal spaces. Make sure your pastures are still along the river. I'm going to draw a river, and that river is going to be in blue. I'm going to draw my pasture. Pay no attention to the dogs growling in the background. They're wrestling. So here's my pasture. There's a rectangle. And I've got to divide it vertically into 3 equal spaces. So I'm going to draw 2 dividers. And I've got 3 equal spaces. Use the height of my pastures as x. So that's x. That one's x. That one's x. That one's x. And we've got to figure out what this length is. If we had 1,200, and now we're subtracting 4x from this, why that would give us the bottom piece. So the area would be, so the width is going to be 1,200 minus 4x. I'm multiplying that by the height. I might simplify that to say negative 4x squared plus 1,200x. Okay. Part C, the neighbor likes the idea and wants to use the same design to have 8,000 square yards of pasture. So that's the area. So 8,000 is equal to negative 4x squared plus 1,200x. I might divide this whole thing by negative 4 to start things out and bring everything over to one side. And that would give us x squared minus 300x minus, dividing this by negative 4, 2,000. And that's equal to 0. In solving this equation for part C, You could use the quadratic formula, that would be fine. There are going to be two different dimensions or two different widths that give you a value for this. If you have a graphing calculator, you could plop this into y equals in the graphing setting and do second calc 0 if you zoom out far enough to be able to see what values you're looking for. I'm going to add the Desmos graph that I made for this so that we can see what this looks like. Okay, this graph gives us an idea of what this function is. It has a 0 at 6.822 and another one at 293.178. So that tells us that either we can have really, really thin 6.822 yards or really, really steep verticals here that are going to be almost 300 yards long each, leaving very little space for this to be narrow. So this is, either way, this is probably a pretty terrible fence, which is what I get for choosing a random number. Let's see if I can zoom out from this. Oh, good, I can. So that's going to go, I'm going to make that go like here. So it doesn't cover anything up. And then for the maximum area of the pasture, I'm going to go back to my original equation, and that was the area, or the y value is equal to negative 4x squared plus 1200x. And what we're looking for the maximum area is the vertex. We've got a couple different ways of doing that. And I'm going to load another Desmos picture to talk about what those two different ways are. The first is in looking at our graph. You might notice that we have a couple of zeros. In fact, one 0 is going to be at 0, another is going to be at 300. And exactly in the middle of those two x-intercepts, I happen to have the highest point. And that happens at an x value of 150. So that's way number one. If I find the two x-intercepts, and for the ones that we're looking at, these are not going to be too hard to find, halfway between them is going to be the highest or lowest point. At some point, you may also have learned that the x value of the vertex is equal to negative b over 2a. That's what's going on here. And that's also the first half, or first piece, of the quadratic formula where x is equal to negative b over 2a. That's the vertex, plus or minus all the other stuff. All the other stuff just zeroes in on the other pieces. The negative b over 2a is what gives you the identity of the vertex. If you have a graphing utility, in other words, a graphing calculator, and you wanted to graph this, notice the scale is enormous at this point, but you could just put this in y1 is equal to negative 4x squared plus 1200x. You're going to have to set your window so you can see the entire graph nicely. And then you're going to do second calc, and you're looking for a maximum. And working through that to find that. So x is equal to 150 for our maximum x value, or maximum y value. I'm going to zoom this guy out, and maybe I'll move this guy over a little bit more, so we have a little bit more room for our lovely pictures. And finally, let's plug that in. So we know that x is equal to 150. That's going to be those vertical pieces. So each of these is going to be 150. And if that's true, that's 600 in total. That means that this bottom part is going to be 600 in order to make this thing 1200. To find the area, that's going to be 150, my height, multiplied by 600, my length, and that gives me an area of 90,000 square yards.